Hi guys, Professor Barber here. This lesson is titled Modeling with Equations. We will build mathematical models or equations to solve common algebraic applications. Upon successful completion of this lesson, you will 1. Be able to build and use models to solve common algebraic applications. Applications include problems about 2. Interest, 3. Area or length, 4. Mixture problems, 5. About time to complete a job, and 6. Problems of distance, rate, and time. 1. Guidelines for modeling with equations. While there is no surefire set of rules that guarantees you'll be able to solve every equation, we do have a guideline that tends to work for most of the types of equations you'll see. The first step is 1. Identify the variable. That means identify the quantity that the problem asks you to find. This quantity can usually be determined by careful reading of the question, and it is usually posed at the end of the problem. Then introduce a notation for that variable. Call it X or some other letter that might be more identifying. 2. Translate words to algebra. Read each sentence in the problem again and express all the quantities mentioned in the problem in terms of the variable you defined in step 1. To organize this information, it is sometimes helpful to draw a diagram or make a table. 3. Set up a mathematical model. Find the crucial fact or facts in the problem that gives a relationship between the expressions you listed in the previous step and the variables you identified. Set up an equation or model that expresses this relationship. 4. Solve the equation. When you do solve it, your answers should be expressed as a grammatically correct, complete English sentence that answers the question posed. And very importantly, step 5. Check your answer for reasonableness. Before deciding that you are done with the problem, consider the reasonableness of your answer, even if your model is correct and your solution process is correct, it is still possible that the answer may not make sense. You must apply critical thinking to ensure that your answers make sense in the context requested. A rectangular building lot is 8 feet longer than it is wide and has an area of 2,900 square feet. Find the dimensions of the lot. Let's start with the fact that we are talking about a rectangular lot. We know that the area of a rectangle is given as the product of the length times the width. In the diagram, I will identify the shorter side as the width and the longer side as the length. The problem statement informs us that the length is actually the width plus 8 feet more. Upon reading the problem further, we also understand that the area has 2,900 square feet, and that is equal to the product of the length times the width. Now let's get this equation into one variable. So I'll write this as 2,900 equals, and where the L is, we'll replace it with a W of W plus 8 times W. Let's continue with this. I will write and distribute the W, so W squared plus 8W equals 2,900. To solve a quadratic, it has to be set equal to 0. This can be written as W squared plus 8W, then subtract 2,900 from both sides. Now that's equal to 0. This factors nicely into a product of binomials of W plus 58 times W minus 50, and that's set equal to 0. Using the zero product property, we know that each of these factors must equal 0. That is, W plus 58 equals 0, and W minus 50 equals 0. It looks like we may have two values for W. Solving the first equation, we get W equals negative 58. The second one, we get W equals 50. Since we are talking about a physical building, we know that the negative 58 does not make sense. That gets thrown out. Now we have a measurement for one of the sides of the dimensions, which is the W. Earlier, we determined that the length L is equal to the width times 8 feet. We solved the width to be 50 plus 8, so the length is 58. The dimensions of this lot are 50 feet by 58 feet. If Taryn invests $5,000 at 4% interest per year, how much additional money must he invest at 6.5% annual interest to ensure that the interest he receives each year is 4.75% of the total amount invested? This is a financial interest problem, so we need a financial interest formula. The one we'll use is for simple interest, which is I equals P times R times T. The capital I is for interest, the capital P is principal or the amount invested, R is the rate in decimal form, and T is time. Since this problem is specific to 1 year, it says annually, we know that T equals 1, so we can simplify the interest formula to just I equals principal times the rate. What we are looking for is the additional money he must invest. So that would be the P. The P is what we're looking for. How much? At 6.5%. Now let's set up the relationship. He will have a certain amount of money, interest earned, at 4%. He will also have some interest earned at 6.5%. And what we want to do is make sure that the amount he ends up with, that interest, is equivalent to earning 4.75%. Having this information in the financial interest formula, let's replace these variables with numbers. For the first, interest at 4%, he invests $5,000, and 4% in decimal form is 0.04. Now, for the interest at 6.5%, we don't know the amount that's going to be invested. So that'll just be P, the unknown principal. 6.5% in decimal form is 0.065. And that'll be equal to the total interest investment amount is going to be the 5,000 plus the unknown principal. Then we need to multiply that by 4.75% in decimal form. That would be 0.04, and for 3/4, that's 7.5. Now we have an equation and we can solve it. Multiply the 5,000 and the 4% together. That'll be 200. The next term kind of remains the same, so we'll just write 0.065p equals. Let's distribute the 4.75% to each of the values in the parentheses, 5,000 and p. 5,000 times that interest rate is 237.50, and when we multiply the 0.0475 to p, we just write 0.0475 times p. Now let's combine like terms. I'm going to subtract the 0.0475p from both sides. When I do that, 0.065p minus the 0.0475p becomes 0.0175p. Let's subtract the constants. We've got 200 on the left-hand side, 237.50 on the right-hand side. Subtracting 200 from 237.50 will give us 37.50. Now we can solve for P. P is equal to 37.50 divided by 0.0175. That quotient is 2142.857. Remember, we are working with dollars. So to answer the question, we would say that Taryn must invest, so must invest an additional, rounding this answer to the full cent, would be $2,142.86 at 6.5%. A woman who is 5 feet 6 inches tall wishes to find the height of a certain 4-story building. The woman measures its shadow and finds it to be 27 feet long, while her own shadow is 3 feet long. How tall is the building? In identifying the variable, or what we're looking for, we are looking for the height of the building. So let's let H equal height of the building. We also have some useful information, but the first thing to note is if we draw this, we'll let this be the height of the building and I'll call it H. The problem further tells us that it casts a shadow that is 27 feet long. Now the woman is 5 foot 6 inches tall. That would be 5.5 feet. We want to make sure all of our measurements are in the same units. So we have a woman who is 5.5 feet tall. 5.5 feet tall, who also casts a shadow of 3 feet. Now we're going to use similar triangles to set up the ratios. What this tells us is that the height of the building casts a shadow of 27 feet, and a woman who is 5 foot 6 inches, which would be in decimal form 5.5 feet, casts a shadow that is 3 feet long. Now we have a set of equations that we can solve. Solving for H, multiply by 27 on both sides. You've got 5.5 divided by 3 times the 27. This will simplify to 5.5. 27 thirds is just 9. And the product of 5.5 and 9 is 49.5. So we say that the building is 49.5 feet tall. Remember to keep the dimensions in place when you express your answers. Stan and Hilda can mow the lawn in 40 minutes if they work together. If Hilda works twice as fast as Stan, how long does it take Stan to mow the lawn alone? So the unknown, or the variable that we are looking for, is Stan's, so we'll let S equal Stan's time. Stan's time. The instructions further tell us that Hilda works twice as fast as Stan, so Hilda's time would be twice what Stan could get done. On work problems, we set this up so that we have the portion done by one person. So we'll do portion done by, let's let Stan go first, plus the portion by Hilda, working in fractional forms, will get us the portion of the entire job. So the portion done by Stan would be denoted by 1 divided by S, plus the portion done by Hilda would be 1 divided by h, and that would be equal to 1 divided by, if it takes them 40 minutes, then fractional portion would be 1 over 40. Let's replace the h in terms of Stan's work, so we'll write this again as 1 over Stan's work plus, and where h is, that's equal to 2s, so 2 Stan's equals 1 over 40. We can simplify this expression 1 over s plus 1 over 2s equals 1 over 40 by clearing the fractions. I would multiply this through, let's see, by, let's do 40 and 1s. So distributing, continuing, 40s times 1 over s is 40 plus 40s divided by 2s. 40 divided by 2 is just 20. The s's cancel. And 40 times s divided by 40 is just s. Well, how nice is that? When we solve this, you get 60 equals s, Stan's time. So we can say that Stan will take 60 minutes to mow the lawn alone. Two cyclists 90 miles apart start riding towards each other at the same time. One cycles twice as fast as the other. If they meet 2 hours later, at what average speed is each cyclist traveling? This is a uniform distance problem, which means we need the uniform distance formula. It is known as D equals RT. D is the distance, R is the rate, and T is the time. The cyclists are 90 miles apart, and so they are traveling towards each other to cover 90 miles of distance. The problem asks for the average speed of each cyclist, or the rate. So we need the rate of one cyclist, and we also need the rate of the other. I'll use R1 for one of the rates and R2 for the other. Now, we are told that one goes twice as fast as the other, so we're going to let R1 equal, say, twice the speed of R2. The uniform distance formula tells us that when you accomplish 90 miles of distance, each of these, one travels a particular portion of the 90, the other cyclist, the other, so D1 plus D2 equals 90. We'll replace the D notations with what it's equal to, R and T. So for the distance of the first one, this guy cycles for 2 hours at one particular rate. This other guy also cycles for 2 hours at a slightly different rate, and they go 90. Let's replace the R1 with its equivalent 2 times R2. So the first term becomes 2 times 2 R2 plus 2 R2 equals 90. This is a linear equation. We can add the terms on the left-hand side. 2 times 2 gives us 4 R2 plus 2 R2. 4 and 2 will give us 6 R2 equals 90. We can solve for the rate of the second guy, which would be 90 divided by 6, and that is 15 miles per hour. We can solve for the rate of the first guy, which we know is twice the rate of the second one, so 2 times 15 would be 30 miles per hour. We say that the average speed of the cyclists are 15 miles per hour and 30 miles per hour. Now this finishes a textbook portion of the problem, but I do want to encourage you to think about the reasonableness of this answer. The 30 miles per hour seemed a little extreme to me, so I did a little research and found out that most cyclists on average go 10 to 12 miles per hour on long distances. Those with reasonable experience go 16 to 19 miles per hour, and the average professional goes about 25 to 28 miles per hour. Here we use the right formula, the right setup, the correct computation, got the correct numbers, but the answer itself does not really make sense in the real world.